Hey there, Mustangs. Welcome back to another edition of No Here, No Problem. Today, we've got a lesson on rational functions and asymptotes and the graphs of these. Before we dive in, I got a question for you. Why don't skeletons go trick-or-treating? Because they have nobody to work with. No, wait. They have nobody to go with. I'm terrible at telling jokes. No body to go with. Get it? Get it? Ah? All right, anyways. So today we're going to be wrapping up this unit on functions and polynomial functions. And today we're going to be doing rational functions. You're going to see in this objective how using synthetic division or using long division is going to actually help us with finding the graphs of these rational functions. Remember, whenever we say rational, we're saying that there's fractions involved. And then when we say asymptotes, there's going to be three different kinds of asymptotes, that we're going to talk about. We're going to talk about vertical, which we've mentioned in the past. We're going to discuss horizontal so you have a better understanding of what's actually meant when we say horizontal asymptote. And then we're going to talk about slant asymptotes, okay? So let's get started on these. So the first thing we're going to talk about is a vertical and a horizontal asymptote. Now, these right here are very wordy. I don't like these definitions. What I'm going to do is I'm going to actually give you some realistic things, okay? When we're talking about a vertical asymptote, which we'll just call VA, okay? A vertical asymptote is a restriction in the domain, meaning that x cannot equal a certain value, okay? So that's what the restriction is. So when I say what's the vertical asymptote, you would say x is equal to that number. So for example, if I said like 1 over x minus 1, it's a rational function, and we say that f of x is equal to 1 over x minus 1, we know that in this case, the domain restriction here is that x simply can't equal 1, right? So if I was to say to you, well, what's the vertical asymptote? You would say x is equal to 1. If we looked at the graph of this, and we were to go to x is equal to 1, we would see that there's this imaginary vertical line that x equals 1 right here. And then we would see that the graph itself is going to look something like, oh God, that was terrible. It's going to look something like this. It's going to follow there, and then it's going to be up here, okay? So that's a vertical asymptote. Now, what about when we talk about a horizontal asymptote, HA? This definition is completely different. This has nothing to do with restrictions on the graph as far as like what it can't or can't equal. A horizontal asymptote is another way of saying the end behavior. Okay? The end behavior. And when we say the end behavior, we're saying what happens as x gets really large. Okay? So when it gets to its largest possible value. Or what happens when x gets really small? Okay, so the largest possible x value and the smallest possible x value, what's happening? And so what we're really saying is the limit as x approaches infinity, what's the y value going to approach? And the limit as x approaches negative infinity, what's the y value going to approach? It has nothing to do with restrictions. It's just what happens to my graph as the x gets really big or as it gets really small, okay? Now, we're going to talk about that in a moment when we get into these problems here, but the horizontal asymptotes, we have a couple different situations that might come up here. We might have a problem where it says f of x is equal to, and we'll see like x squared plus 5x plus 10 over, I don't know, let's say 4x squared plus 3x minus 2, okay? So think about what this means as x gets really large here. What's going to end up happening? If x gets really large, let's say I put in like for this x value that's right here, let's change these x values. Let's put in there that x is equal to like 1 million. X is just big, we'll make it 1 million. So 1 million squared, 5 times 1 million plus 10, okay? And that's going to be divided by 4 times 1 million squared plus 3 times 1 million minus 2. So just totally make it up a trivial value of x. Let's see what happens when we simplify this a little bit, okay? So here's what's going to happen. If we look at this situation here, this value is going to be really crazy big. I mean, it's going to have 12 zeros in it, whatever that number is, okay? So try to imagine if you have, I don't know, let's just think about a really big number. Let's say that I have like $5 trillion, okay? If I was to lose $10 from that really big number, does that 10 really make a difference? It doesn't. If I was to say I had $10 trillion and I lost 5 million, does that really make a difference? No. And so what happens is when we're looking at the end behavior, as this X is really large, overall what's going to happen is these values that we see right here, they're not going to really make much of a difference. They don't have much of an impact on this really large value that's over here on the left. So what we say is, well, these values right here, they're not really going to mean much. They're going to kind of actually go away. We can kind of ignore them for all intent purposes. Same thing with this right here. That -2 in the grand scheme of an extremely large number isn't going to matter. Same with that 3 million, so we can kind of ignore that. So then what are we supposed to focus on here? Well, look at what happens here. We have this 1 million squared, and then we have 4 times 1 million squared. And what's going to happen is these million squares are just going to actually cancel each other out because they're exactly the same. What are we left with? We're left with a 1 over this 4 that's right here. And so if I was to say, what's the y value as x gets really large? It's pretty simple. It's going to equal this value that's right here and this value that's right in front of here. It's going to equal this 1 over 4. So as x gets really large, my horizontal line is going to approach 1 over 4. That's it. That's the horizontal asymptote. Now that one only works when we have the degree exactly the same on the top as on the bottom. If the degrees are exactly the same, we just take the coefficients of those leading terms. Okay. What happens if in the event that we don't have them exactly the same? Well, there's 2 scenarios that are going to come up with this. The first one is when we have f of x is equal to like 3x minus 5 and over 5x squared plus 2x minus 4, whatever, okay? What's happening on this one is when we look at it, the degree of this one is equal to a 1, and the degree of the bottom one is equal to 2. So we get a situation where the top is actually smaller than the bottom. So what's going to happen is x gets really large. Well, let's go back to that scenario that we just said, where if I took that x and made it into another million, and then minus 5, and then I've got a 5 times 1 million squared plus 2 times 1 million, okay, and then minus 4. What's going to happen is we have that situation again where on the bottom here, well, let's talk about the top. This right here is going to be 3 million. If I had $3 million and I lost 5, does that really make a difference? No. That 5 doesn't really make much difference here, okay? When I look at this bottom part and we say, well, we have a really huge number here. Again, we've got 5 with 12 zeros after it. Does $2 million really make much difference? No. Neither is that minus 4. So what's going to happen is we can basically ignore all the other stuff that's outside of there and let's just focus on this stuff right here, okay? Now, what's happening? If we focus only on this part right here, we have 3x over 5x squared. If I simplify this, this is really going to just be 3 over 5x. Now watch what happens. Let's pretend like these are just even smaller numbers. These 3/5, it's close to 1. Let's just say it's 1, so 1 over x. Let's say as x gets really big, watch what happens. Let's say I make x equals 1 over 10. That's going to equal 0.01. Nope, 0.1, sorry. Let's say that that is 1 over 100. That's going to be 0.01. Let's say it's equal to 1 over 1,000. Notice that x is getting bigger. It's equal to 0.001. Let's say it equals 1 over 1, 2, 3, 4, 5, 6. This is going to equal 0.0000, 10, 100,000, 10,000, 100,000, million. And what's going to happen is as this x gets really large, my decimal is going to get to where it's at 0.000000 zeros, right? Lots of zeros. What's really happening is my y value is getting closer and closer to 0. And that would be my horizontal asymptote here, is that y is going to equal 0. So when we have a degree on the top is 1 smaller than the degree on the bottom, we end up with a horizontal asymptote of y is equal to 0. And then we've got this third scenario. The third scenario is when the top is actually 1 bigger than the bottom. And we're going to get to that in a minute. So let's start talking about these problems here. We say find all the asymptotes of the given functions and then state the end behavior. So let's look at this first one here. We have 2x. Look at the degree here. This degree right here is equal to a 1. This degree right here is equal to a 2. Now we have that situation where the degree on top is actually 1 smaller than the bottom. So if we look at that, we look at this and we say, all right, we got 2x over 3x squared. We can ignore that 1 because remember that 1 that's right there, this little 1, it's kind of useless in the grand scheme of things. It doesn't really impact anything as x gets really large. So what would happen is we end up with a 2 over, these x's will cancel, and that's no different than the situation where we just said we get 2 times 1 over x. And what's going to happen is x gets really large, y is going to approach 0. So this is my horizontal asymptote. And if we were to state the end behavior, we would say the limit as x gets really big, my y value is going to approach 0. And as x gets really big in the other direction, my y value is going to approach 0. It's the same thing in both directions, okay? For the domain restriction, we look at this and we say, are there any restrictions? Can 3x squared plus 1 equal 0? Well, it's not allowed to equal 0. If I solve for this, we get 3x squared cannot equal -1. X squared cannot equal -1 over 3. And what's going to happen is I'm never going to have a square equal negative. So if I take the square root of this, we're going to get plus or minus root 1 over 3i. There's no restrictions here, so there's no vertical asymptote. Okay, so there's no vertical asymptote here, and we have a horizontal asymptote at y is equal to 0. Let's confirm this when we look at it. Okay, here's the graph of this function. Oops, hang on, I got to turn this graph off down here. Here's the graph of this function, and if I was to graph that y is equal to 0, you would see, let me change the color on that, you would see that what ends up happening is my graph doesn't have any vertical lines that's following. There's nothing going up and down that my graph actually follows here. You can see, I'll zoom out all the way. You'll see there's no vertical lines because there's no vertical restrictions here, okay? However, what happens as x gets really big, look at the blue line that, I don't know if you can see, it's populating right there in the middle of the screen. But what's happening is, maybe I can make this denser. Let's make this 5. There. Oh yeah, let's go 8. Nope, too big. Whoa, what was I thinking? Let's go 10. Okay, so you can see there's the asymptote. All right, now I'm going to zoom out so you can see that as we look all the way to the right, you can see my graph just stays along this graph. It doesn't go above it or below it. Same thing with as we go to the left. As x gets really big, it approaches 0. As x gets really small in the negative direction, it approaches 0. Okay? And then there's my graph kind of going along that asymptote. All right, let's go ahead to the next problem here. So we have a situation in this one where we have a denominator. Let's do the vertical asymptote first. Okay, so the vertical asymptote, we know that x squared minus 1 cannot equal 0, right, because that would make it undefined. X squared cannot equal 1, so x cannot equal a 1 or a -1. So my vertical asymptotes in this would be x equals 1 and x equals -1. Two vertical lines here, x equals 1, x equals -1. Let's look at the horizontal asymptotes. Okay, the degree on the top is exactly the same as the degree on the bottom. And when we look at that, remember we said we can just completely ignore this 1 right here, this -1. And what the problem becomes is, well, y is going to equal 2x squared over x squared, which means that these cancel, and as x gets really big, my y value is going to approach 2. So let's see what this graph looks like. Okay, there's the graph. There's an asymptote. There's an asymptote. There's the horizontal asymptote. Now, I'm going to zoom out so you can see the rest of this graph, okay? You can see right here that what ends up happening is my graph has those two vertical lines right there where my graph is following it, but it doesn't cross it because it can't equal that. And then you'll notice the horizontal line that's right there. What happens is as my graph moves to the right, it approaches this value. It approaches 2. And as my graph moves to the left, it approaches 2. And it never crosses it there. Not that it shouldn't cross. It will cross sometimes, but it's just saying it approaches the end behavior here. Okay? So if we were to say, what's the end behavior of this? F of x, the end behavior here is the limit as x approaches infinity, the y value is going to approach 2. And the limit as x approaches negative infinity, the y value is going to approach 2. It tells us the same thing in both directions. Okay? All right, let's go on to another one here. So now this is where we talked about what happens if the degree on the top is actually 1 bigger than the degree of the bottom. Okay? We have the 2 on the top, and we have a 1 on the bottom here. What happens in this instance? Well, let's look at the graph and see if we can figure out what's going on here. Okay? Turn those off. There we go. There's our graph. Now look at my picture here. Look at the behaviors on the right and to the left. What happens is to the right here, it's not going horizontally anymore. It's not going to the right horizontally. It's actually going on an angle up and to the right. And if I look to the left, it's going on an angle down and to the left. So this is what we call a slant asymptote or an oblique asymptote. You can tell that there's going to be a vertical line that my graph will follow up and down. That happens when x is equal to -1. Okay? Well, why is that? Why do we get a vertical one, and how do we get that diagonal one? Well, let's talk vertical asymptote first. The vertical asymptote here happens because x plus 1 cannot equal 0. So x cannot equal -1. That means my vertical asymptote is x equals 1. Okay? Easy peasy on that one. The horizontal asymptote, we never have a horizontal and an oblique. We can only have one or the other. In this case, we have a oblique asymptote because the degree on the top is 1 bigger than the bottom. So let's go ahead and do this. Now, to get that slant asymptote, we use long division or we can use synthetic division. Since this is linear right here, I'm going to go ahead and use synthetic division. So this top part is x squared minus x plus 0. So I'm going to use a 1, a -1, and a 0. Okay. And then we're going to have, for the outside value, we're going to use a -1. And that's just synthetic division. We're going to bring down the 1, multiply, we get a -1. This gives me a -2. Multiply, we get a 2, and that gives me a 2. There's my remainder, excuse me. So what's the slant that we're looking for? Well, believe it or not, it's actually this part right here. That is my slant asymptote. That right there, if I graph this, will give me a diagonal line with a slope of 1 and a y-intercept of -2. So let's confirm this. Look at what happens when I graph that line. Y equals x minus 2, and as I zoom out, you'll see my graph is following this behavior. Traces it out. Okay? So then if I was to say, well, what's my behavior that's happening here? Well, we just saw this, that my graph looks something like this, and my graph looks something like this, right? And we say, well, as my graph is going, as my graph is going to the right, what's the behavior? So the limit as x approaches infinity, so as my graph goes to the right, you can see my graph is going right and up. So my end behavior for this is it goes to infinity. And my behavior on this other one is as x gets really small, or really negative, so as it goes really far left, you can see my graph is going left and down, so that means that f of x is going to equal negative infinity, going down. Okay? All right, let's do a couple other ones here. We're almost through. It's just examples at this point. So this one says, find all the asymptotes of the graph, and then state the end behavior. Let's see what we got here. You ready? Looking at my top here, we've got x plus 5 and x minus 2. That's the denominator factored out. So we get that x is equal to -5 and x is equal to 2 are my vertical asymptotes. Okay, so we're going to have 2 vertical asymptotes for this problem. Now let's look at it and figure out. Let's look at and figure out what is the horizontal asymptote. Well, since my degree on the top is 1 bigger than the degree of the bottom, we don't have a horizontal asymptote. We actually have a slant asymptote. So now let's go through and figure that out. I can't do synthetic division here because this is not linear. I have to use long division, unfortunately. And this is actually still pretty quick. So we have 3x cubed, 2x squared. We have no x's, and then we have that -8. And if we go and divide by that x squared plus 3x minus 10, let's go ahead and do the long division. X squared goes into 3x cubed, 3x times. That's going to give me 3x cubed plus 9x squared minus 30x. Okay. Opposite, opposite, opposite. We end up with a negative 7x squared and then a positive 30x. Bring down the 8. How many times does x squared go into negative 7x squared? It goes into it negative 7 times. So we have negative 7x squared, then we have negative 21x, and then we have positive 70. Now at this point, we don't care about anything else. I could actually stop. I've got the part that I need, which is right here. This is the part that's going to generate my slant. We're going to have that y is going to equal, y is going to equal 3x minus 7. So my slant asymptote in this is y equals 3x minus 7. You have to say the y part. Okay, let's look at the graph of this. Okay, so here's the graph. All right, let's zoom out so we can see the entirety of it. Let's go in through my slant. You can see that my graph actually follows that. Okay, I'm going to even spread this out a little so we can see a little better. Okay, I'm going to zoom back in now that we saw the slant asymptote. Let's look at my vertical asymptotes here. X equals negative 5 and x equals 2. And you can see that my graph follows those. And now if I was to say to you, whoopsie doodle, what was it, negative 5? There we go. Oh. Oops. Whatever. If I was to say to you, okay, what's the behavior that's going on here? Well, you look at the right end of the graph, and you can see it's going to the right and it's going up. And if we look at the left end of the graph, it's going left and it's going down. So the end behavior from this is that the limit as x, I don't know what that m is there. The limit as x approaches infinity, so as x goes to the right, my graph goes up. And as x goes to the left, my values go down. There you go. There's your end behavior and your asymptotes. All right, so let's continue on here. So graphing irrational functions, let's find all the behaviors, the intercepts, the holes, all that jazz. Now there's a new thing in here talking about holes. I'm going to talk to you about that in 1 second. Let's get through all the other stuff first here, okay? So when we look at the denominator here, the vertical asymptotes from this are going to be when the denominator is equal to 0. So 2x squared minus 17x plus 30. Okay. We're going to do guess and check here. So I'm going to go with 2x and then x. I know that that's going to have to give me 2 because my leading term is 2. So those are my only factors there. The values for 30, I'm going to use a 15 here and a 2 here. No, I don't like that. Let's go with what? 5, 6, 7, 10, 3. So, well, sorry, hang on. 1 and 30, 2 and 15, 3 and 10, 5 and 6. All right, if I put a... No, that's not going to work. What are the values that we're going to put here? 6 and 5? It's going to be 12 and no. If I put in, oh, here. 10 and 3? No. 2 and no. What are the values here? What am I missing? 1 and 32, 15, 3 and 10, 5 and 6. Let me cheat, go back here. I said 2.5, 2 and 5. This is 5 and this will be 6. Oh, doy. Okay, so sorry. So this will end up being, if I do this, they both have to be negative. That's what it was, okay? And so what's going to happen is the 2x and the x will give me 2x squared. The 2x and the negative 6 will give me negative 12. The negative 5 and the x will give me negative 5x. So Everything checks out here. So we end up with x is equal to 5 over 2, and we end up with x is equal to 6. Those are my vertical asymptotes. Okay? We look at the degree on the top, and we look at the degree on the bottom, and aha, we don't have to do any long division or synthetic division. The degrees are exactly the same here. And what's going to happen is we're going to have a horizontal asymptote at y is equal to 1 over 2, because that's just taking the 1 and the 2 that we see right here and reducing it. It's just y is equal to 1 over 2. Okay? Now, let's get to some other parts here, okay? It says the possibility of a hole. What is a hole exactly that takes place in a problem? Well, if I factor out my numerator, we're going to have x minus 6 and x plus 2. And when we factor out the denominator, we already had 2x minus 5 and x minus 6. And a hole is actually when we have discontinuity in the picture that's removable. So what that means is that when we look at the top here, you see these x minus 6s that are on the top and bottom, we can actually get rid of them. And what's going to happen is that x minus 6 that was previously a vertical asymptote is now eliminated, and it's going to become what we call a hole. It's a hole in our actual picture. So this is no longer VA. This is actually a hole at, oops, it's a hole at x is equal to 6. Okay? Huh? What does that look like? Well, let's take a look at our picture here. Okay, let's turn these previous ones off. And let's look at this new one here. So we've got an asymptote, and let me get this graph here, at 6. And then we've got y is equal to 1/2. Now I'm going to zoom in on this so we can see a little bit better. Okay. And you can see here that there's we got that 5 over 2 that we talked about for the vertical asymptote there. We've got the horizontal asymptote, which is y is equal to 1/2, which you can see my graph follows it. But look over here. Look right there at my graph. Why does my graph not follow that spot exactly? What happens? Well, it said that there's a hole in my picture. What does that mean? Let's zoom in here and see what's going to happen. I'm going to turn this off, and let's zoom in real close so we can see. Now I'm going to trace along here so that you guys can actually see a value, okay? I'm going to trace along to where x is going to equal 6. Ready? We just jumped over it. There you go. You see how it keeps saying undefined? I can't get it to stop. Oh, God. All right, there it is. You saw it. There it is. What happens is my graph is undefined when it's equal to 6. And so instead of us getting a vertical asymptote, you see it like pops up this little hole right there. Oh, all right. But you get the idea is that right there at 6, we get this little hole in my picture. All right. There it is. There's the hole right there. It's undefined at that spot. There's a hole. There's a removable discontinuity in my picture. So there's a hole when x is equal to 6. Okay. Let's talk about the other parts here. The end behavior. End behavior. So again, that's going to mirror our horizontal asymptote. So the limit as x approaches infinity, my f of x is going to approach 1/2. My limit as x approaches negative infinity, my f of x is going to still approach 1/2. Okay. And then let's do the intercepts, okay? So the x-intercept always happens when the numerator is equal to 0. Okay, so the x-intercepts happen when the numerator is equal to 0. So if we have x minus 6 and x plus 2 is equal to 0, that x minus 6 got eliminated from the problem because it got wiped out by the denominator, which means that we're simply going to have x is equal to -2. So -2, 0. And if we look at our picture, we'll see at -2, I got to zoom back out here, at -2, you'll see my graph crosses right there at -2, 0. Okay. For the y-intercept, that is even easier. The y-intercept is just as simple as taking all my x's and crossing them off. The reason we can do that is because the y-intercept happens when x is equal to 0. So if I cover this up, cover this up, cover this up, and cover this up, those mean that x is equal to 0. We have negative 12 over 30, which will reduce. So we have 0 and then negative 12 over 30, which I can reduce that, and it's going to become 0 divided by 6, so it's negative 2 over 5. Okay, so my y-intercept is 0 and then negative 2 over 5. Whew! A lot of stuff going on here. Okay, couple more problems. All right, 2 more, and then we're going to be done. All right, so we're going to go ahead and sketch the graph of this, identify all the intercepts and holes and behavior. Okay, before we start, I'm going to go ahead and factor this out so we know what we're working with. X squared minus x minus 2 over x minus 1. We have f of x is equal to x minus 2 and x plus 1. Okay, and then we have this x minus 1. Nothing cancels in this, so there's no holes. Okay, my vertical asymptote is my denominator, so x equals 1. My horizontal asymptote, is that there's none. That's because the degree on the top is 1 smaller than the degree on the bottom. So that tells us we're going to have a slant asymptote. The slant asymptote, if we go through and do this, is going to be 1, negative 1, negative 2. We're going to use a 1 for the 0. That comes from my denominator. This will be 0, and then 1, and then negative 1. This right here is my equation, so y is equal to x. Okay. My x-intercept is going to be the numerator. So that means we're going to have x minus 2 and x plus 1 is going to equal 0. So that means that x is equal to 2 and x is equal to negative 1. So we're going to be at 2, 0 and negative 1, 0. And then the y-intercept is when all those x's are equal to 0. So if we have this equals 0, this equals 0, this equals 0, we end up with a negative 2 divided by negative 1, which is just a 2. So we're going to have x-intercept at, y-intercept at 0, 2. The end behavior for this is, well, let's look at the graph. Oh my gosh, I forgot to graph it. We have y is equal to x squared minus x minus 2. So I gotta put the graph in here now. X squared minus x minus 2 divided by x minus 1. Okay, and we can see from the slant here, we said that y is equal to x. Okay, and from the slant, my graph goes up and to the right, down and to the left. So the behavior here is that f of x, as the limit, the limit as x approaches infinity, my graph goes up. And the limit as x approaches negative infinity, my graph goes down. There's all your behaviors from that graph. Okay? All right, and one more just for good measures. And this one simply just says state the end behavior. That means all I really have to do is just look at this part right here. And we know the degree on the top is the same as the degree on the bottom. So that means we have y is equal to 2 over 4, which is just 1/2. So the limit as x approaches infinity, my y value is going to approach 1/2. And the limit as x approaches negative infinity, my y value is going to approach negative half. No, what am I saying? 1/2. Okay, so it's going to approach the same value for the horizontal asymptote. Okay. I do want to talk about one more quick thing, and this is, I'll mention in class because I guarantee you guys are going to listen to the entirety of this. What happens when I give you a limit where I say this, 1 of, x minus 2. And we say that the restriction at x is equal to 2. And I can look at this graph and know that the graph is going to look something like this. That there's going to be, this is where x is equal to 2. The asymptote for the y is going to be like this. And my graph is going to actually look something like this. Okay, so here's a new notation for you. Ready? The limit as x approaches 2 plus, and the limit as x approaches 2 minus. Now this is the new notation. This notation says, when we look at this, that as my graph approaches, as my x approaches 2 from positive, meaning it comes from the right. So what this means is as my graph comes in from the right, so it's coming from the right side in, what's happening to my graph is going up. So as it approaches 2 from the right, it's going up. So that means my graph is going to approach infinity. Versus when we look at the other one where it says as x approaches 2 from the left. So as I come in from the left and I approach this value, my graph is going down. That tells us that my graph is approaching negative infinity. So I'm giving you a heads up. This is going to be an extra credit question on your quiz, okay? That is it, everybody. It's a lot. There's no doubt that this is a lot. Go back, look at it, ask questions, but it's an easy section, but there's a lot of little details to try to keep track of, so it can be pretty difficult, okay? You take care. Reach out if you have any questions. Be safe, be responsible, be respectful, and have a good day, okay? Take care.